All right, we're almost there. We've talked about resolution. What is resolution? And that is when we divide a certain number into a certain number of bins, we can only know, within some range, right? And so we want to as engineers, we like to measure things as accurately as possible. But if we've only got so many bins, we've only got so much, resolution or precision with which we can measure things. All right. So let's back up just a little bit. Remember, we said, what's the point of this? Well, with only 256 bins, we can only measure to 1/256th of what we're trying to measure. And the more we spend, the more bins we get, and the better our measurement is, right? Okay, so later on this semester, and I'm going to qualify this with, hopefully, you'll connect a load cell, which is basically a way to measure force, so like an electronic scale, to an NI9219, right? Very expensive little data acquisition module with a 24-bit analog to digital converter in it. So to what precision can we measure this load, right? Well, so we're going to divide it into bins, and our A to D converter is 24 bits. Right, so that means we have a total of 2 to the 24th bins. Right, think my dresser, my wardrobe only has 2 to the 3rd bins. This converter has 2 to the 24th, which equals what is it? I think it's around 16 million. Yeah, so that's 16,777,216 bins. Wow, that's a lot of bins. Right, so I'm going to take my 5,000 pounds, force, divided by 16 million, 216, right? And that means I can measure force down to 0.000298 pounds force. Wow, so that's really using this, a pretty big load cell. I can still measure down to a very, very small weight. Now, 298 micropounds, right? That doesn't really make much sense to many of us. So maybe let's convert that to ounces. Times, let's see, 16 ounces to 1 pound force, right? Pounds force cancel. So then we have 0.004 ounces. Well, that's still not a number we use very often, 4 milliounces. And typically when we're doing stuff in English units, we don't even get this small, but we can multiply that. I think it's 237 grains. Or is it 437? Maybe it's 437 to 1 ounce. The ounces cancel. And so we can measure all the way down to 2 grains. Right, and the grain is some archaic unit of measure that comes from a grain of wheat from the middle of the kernel. But anyway, so that gives an idea when we have really good equipment, really good electronics, we can make very accurate measurements. Okay, so anyway, on to the oscilloscope, right? Oscilloscope, right? This is something that's oscillating. And this allows us to view it, right? So we can take a picture of something that's oscillating, specifically an oscillating voltage signal, right? Well, why are we always talking about voltage signals? So the load cell, this is what we're going to use in class. And so let's see, does this one have any? No, it doesn't have any scales on it. But this measures force, right? And so this might be, this one, just eyeballing that one, looks like it might be a 500, maybe a 1,000 pound load cell. A pressure sensor, right? That helps us in fluid mechanics. Pressure is a huge deal. Accelerometer. that measures acceleration. Does it really measure acceleration, or is actually there a little load cell inside there that measures the force that's on something? Probably the latter. And of course, we're oftentimes interested in measuring temperature for chemical or heat transfer experiments. So yeah, these are all things that give us voltages. These give us voltages, and somehow we have to convert that voltage to a digital signal, and then convert that digital signal to an actual force, temperature, acceleration, or pressure. We'll learn much more about this in Measurements Lab again. And then also in 307, we'll learn a lot more about load cells. In ME307, you'll probably do some of that in your manufacturing classes. We don't actually make a lot of, and then in 370, we'll measure a lot of temperature and pressure stuff here, and you'll need to understand the resolution there too. Okay. So anyway, say we're doing some experiments on crash test dummies, right? We're putting a dummy in a car, we slam the car into a brick wall, and we just measure stuff, right? We know that there's going to be a very rapid accelerations and decelerations, very highly fluctuating forces and loads. So we might have some wildly varying voltage coming from this sensor. Now, here's one that's varying very repeatedly, right? It makes a nice little sine wave. Let's see, let's trace this one out. It kind of makes one period, let's see there, and then it does another one here, and does another one here, and then a little bit more, right? So it does about 1, 2, 3, and 3 1/4 maybe. So this is about 3.25 hertz, right? Which means it's 3.25 cycles per second, right? And so this is some picture of some signal that I want to measure, right? All right, so the oscilloscope gives me a window, right, that I can use to look at this voltage. So I need to control how big the window is, right? How tall is the window, right? Because that's the voltage scale. If I'm measuring something that's like maybe microvolts or millivolts, for instance, the electrical signal coming from the human heart, or am I trying to measure the signal coming into a huge power transformer at the top of a utility pole, right? So I need to control the height of my window. That's in voltage, and that's volts per division. And typically there's 8 divisions there, right? So each division could be a couple millivolts. Each division could be hundreds of volts, right? So I need to scale it that way. Also in the time, I need to know how wide this window is, right? If I'm measuring heartbeats, I might need, say, if you're looking at an elite endurance athlete, their heart might only beat 30 or 40 times in a minute, right? Which means it's a second or two between beats. So I might need a full second there. Whereas if I'm measuring, the impact on a crash test dummy, I might need milliseconds there. So I need to adjust how wide that is, and that is the time. All right. And finally, there's a really important thing here called a trigger, right? I want to say when do I start displaying this data? The voltage is changing constantly. When is it interesting to me, and when do I want to start the recording? When do I want to start the movie? When do I want to start the picture in time, right? So let's say I decide this is the same signal again, right? And it's I get about 3 1/4 cycles in this 1 second. But I'm really just interested in just this part here that's in the red box. So I've got, I want to measure a total of 200 milliseconds, right? So this distance here is 200 milliseconds. And so I've got, there's 10 divisions. So I would want to expand this so to 20 milliseconds per division, right? That way, if each of these, the 10 windows on the display, remember there's 10 divisions here, if each of those 10 divisions are 20 milliseconds, then I get a total of 200 milliseconds, which means I can get this whole interesting part of my signal. Likewise, I know it's going all the way up to positive 3 volts and all the way down to negative 3 volts. And so maybe 8 volts would be enough to get the picture I want. And so I'd make, let's see, there's 8 divisions up and down. And so I'd want to make each one of those divisions 1 volt. So I'd want to make it 1 volt division, 1 volt per division, up and down, and then 20 milliseconds per division left and right, right? So remember, it's always 10 divisions left and right in time, and 8 divisions up and down, like that, right? And then triggering, right? I want to know, when do I start recording, right? If I just fill up the whole screen, right? And so here again is 200 milliseconds. There's 200 milliseconds there. And it takes some finite amount of time for the oscilloscope to reset and then show me another picture. Then I'm going to get this 200 milliseconds. And then my oscilloscope resets, and then I show a picture of this 200 milliseconds. And then I show a picture of this 200 milliseconds. All right, this is all great. Except look what happens. First, I'm starting at 0, and then I go all the way down to like -3. And then I start down at -3, and then I wind up going to about 1, and then I start at about -1.5, and I go all the way up to 3. And then I start at about 2, and I go, down and come back up to about 0. So I kind of took 4 snapshots, or 4 little recordings of this voltage, and I got 4 very different pictures. So it's going to look like this. Right? And I look at this, I'm like, what the heck is going on? Now imagine things are happening really fast, and I've got hundreds of these. It's just going to be a mess. So I need to somehow say, I want to record it in such a way that I get a picture of what one of these waves looks like, or of that one of these cycles looks like. So what do? I say, I'm going to trigger this. I'm going to say, don't start recording, or don't start displaying the signal unless you see a voltage of 2 volts and the voltage is on its way up. All right? So what happens? It's 2 volts. It's on its way up. Right? So then I'm going to get this picture. All right? And I fill up the whole screen because, again, this is still 200 milliseconds. Right? So I fill up my whole screen, my all 10 divisions, 20 milliseconds each. So for a total of 200 milliseconds. I fill up the whole screen. Now, rather than starting the next recording right away, I say, no. Wait until you're at positive 2 volts and an increasing voltage. So it waits until we get here. And we say, 2 volts, yeah, it's on its way up. Display that. So we display that. And then wait, 2 volts on its way up. Display that. Wait. Okay, 2 volts on its way up, display that. Do you notice anything about the voltage pictures that I'm displaying every time? They're always the same, right? So it looks like this. If I have a really nice smooth signal, I will show all these overlapping signals, because I'm always starting at the same place and always starting at the same slope. If I waited until I was 2 volts and on its way down, right, I might actually sometime later start recording, maybe here, right? And then I'd have different pictures every time. So I don't want to do that. I always want to start at the same voltage and the same slope, because that's the most likely to capture the same spot in the cycle. A lot of things in engineering are repeating or cyclic or periodic, and so that's how we want to use the scope, all right? And then I'll get a bunch of overlapping sweeps. So some of the terminology, just in case you're not familiar with this, you probably learned most of these in your trig class. So here is the period is how long is it between repeating things, right? How long does it take to start at the very top and then make it all the way down to the very top again? We decided, well, in this case, it takes about 1/100th of a second, or 10 milliseconds, right? What is the amplitude? How far is it going up and down, right? It starts at 0 and it goes up 1 and it goes down 1, right? So that means it has an amplitude of 1. And the frequency is how many times does it repeat itself per second. And so there I can just use the inverse. The frequency winds up being the inverse of the period. Now there's something very important we'll talk about in the next video, and that is the RMS voltage, or the root mean square. When something goes up and down, 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 what's the average voltage here, right? So the V average, right? Some of you who are real calculus whizzes might be able to look at this and tell me what it is. Or even if you're not, you can just intuit this. It's up about the same time as it's down, so the average voltage here is about 0 volts. Always got to put units on stuff. So the average voltage doesn't really tell me much, it just says it's 0. So any sine wave will have an average of 0. So what we do is we square everything, then we take the average, and then we square root it again. And then we call that a root mean squared voltage. So that stands for, let's do that in blue, root mean square. Right, so we square it, we take the average, and we take the square root. So it's the square root of the mean of the squared voltage. And for a sine wave, it works out to be divided by the square root of 2, right? And that gives you our RMS voltage. Okay, now, we talked about t-shirts and socks and underwear and all this resolution stuff. What does that have to do with the oscilloscope? Let's say I've got this signal, right? And it looks like, wow, that's pretty fast. It finishes a whole cycle in less than 10 milliseconds, it looks like. So it's a very fast, high frequency signal. It's going from 1 to -1, so not a particularly, remarkable voltage, but plus or minus a volt, fine. But say I want to know what's happening right here, right? This is my area of interest. I want to get in there, and it's this nice, smooth sine wave. I want to take a look at what that really, really nice, smooth sine wave looks like if I zoom way in. So I set my divisions, my time per division, my voltage per division setting, so I can zoom way in there and see a nice little picture of that nice, smooth sine wave, and I get this. What? What is this, right? Because this is a digital measurement. It takes me a certain amount of time. So this distance here is some finite time between measurements. Between the measurements. And this distance here is resolution. Right? Just like if I pulled a sock out of my bottom drawer, I know it's good from 0 to 10 degrees, right? And I don't know any more than that. All I know it's good from 0 to 10. So on this particular oscilloscope, I only know that those dots there mean it's somewhere in that range. That's the best my analog to digital converter can do. That's the best my resolution has. And then of course it gets a little noisy in spots like that, it kind of bounces back and forth a little bit. But these are digital measurements. They have finite resolution, and there's a finite amount of time between my individual measurements. And so I'm going to have you guys reproduce this on your when you make actual measurements with your oscilloscope in the lab, right? So if you think that we're getting a nice picture, a nice smooth sine wave, no, you're not. This is a digital measurement. There's a lag between measurements, and then there's a distance between adjacent voltages, right? And that's just the nature of the electronics. For instance, if I had a 2-bit oscilloscope, 2-bit, it's like, get that 2-bit oscilloscope out of here. A 2-bit oscilloscope would mean I've only got 4 bins. So if I'm trying to display this signal here, the nice black sine wave, in reality, my anywhere in here, right? Well, actually, anywhere in here, it's all going to show up as just this voltage right there. Because my oscilloscope, it's only got 4 bins. All of these voltages, right, in that shaded green region, just show up as whatever voltage that is. And so it's going to look really chunky like this. And so if I've got plus or minus 2 volts, for instance, and I've only got 4 bins, I can only narrow stuff down to at best ½ volt, right? Not very accurate. So that's an example. That's what a theoretical 2-bit oscilloscope would look like. Of course, even the cheapest scopes nowadays are at least 6 or 8 bits. But a 2-bit one would be pretty chunky. All right, now data acquisition systems. This is, for both Professor Nellis and I, this is everything for us. We're both experimentalists. We're always doing experiments in our labs, and the quality of our data really, really depends on, the resolution. So here we have a 16-bit, device for $375, right? So that's pretty cheap. Whereas when you get into that 9219 from our previous example, much, much more expensive. So this is a picture of the scope that you'll be using in the lab. We've got controls. We have 2 channels, right? So we can plot like one wave and a second wave, and I might be able to do that in the video. We'll see. It could actually be a little dangerous. And then we can control our time division over here. We can control when we trigger the signal, right? When do we start recording these images? And then there's a bunch of other stuff, other function buttons up there, right? And this is where we're going to see all the important information. And so lastly, don't forget, you've got a pre-lab. Even though Monday's a holiday, engineers don't like holidays. So you've got to work on the pre-lab and have that pre-lab done, ready to go before the lab starts on Tuesday. And it's several pages of reading. It'll probably take about 10 minutes, 10 minutes to do the actual thing. So be ready for that. We will meet in person for those of you who are not quarantined. We'll meet in person in the lab Tuesday, Wednesday, or Thursday. Friday lab, right, is more SolidWorks. We're going to start to work on assemblies and putting a bunch of parts together. So that's what we'll be working on then. That's it for now. I'm going to try to make one more demo video for you. It's not necessary. You don't need the last video, but now you know enough. Do the pre-lab, and we'll see you guys later.